Hey everyone, how's it going? Are you doing good? Hey, how's it going? Yeah, not bad. Not bad at all. Hey, nice to meet you. Feeling good. Good to see some return faces. Uh, Today's about moments. Have people seen much stuff about moments before? Is this a new topic for people, or an old topic you're bored of, or somewhere in between? Or an old topic you're not bored of? Even better. I actually think it's quite a cool topic because it's very kind of real life. M equals FD, got it down. The most important equation. Certainly for moment stuff. In general, it's a pretty important one. It's a kind of a funny one because it's exactly the same looking formula as the one for work done. Yeah. Work done is also a force times a distance. Yes, absolutely. No problem. Yeah, these are two very different distances. Yeah. In work done, it's like the force times the distance traveled in the direction of force. For moments, it's like the distance like perpendicular to the force or something. It's kind of weird. What a moment is. You know what a force is still confuses me. Like what's a force? How do I know how I figure out? I don't know. Forces confuse me. Moments, I'm like, oh, I'm taking this thing I don't understand and multiplying it by a distance. The rule with these things typically tends to be that, like, how is energy made from the start? God, yeah. I mean, depends who you ask. Some people would say it was always there. Some people would say something, quantum fluctuation, something. I'm probably being a bit unkind towards that. I may also think that. Yeah, it's possible. It's not exactly my area of expertise, but I think technically energy can be on small time scales, not actually conserved. So if you look at what happens in a short enough period of time, energy won't be conserved. But as long as you wait for long enough, it always kind of averages out. Yeah, slides, they should be coming. Cool. Yeah, sorry, slides are just coming. Yeah, sorry, I haven't quite got the slides yet. They'll come any second. We might just get going before we have them, but we'll absolutely get them. Like two particles appear and annihilate. Yeah, exactly like that. Actually, that's exactly it. Yeah, quark gluon plasma. Yeah, this kind of stuff. Okay. Okay, sorry that we don't quite have the slides just yet. I'm going to start us off on the session. Yeah. Cool. Awesome. There we go. There's the slides. And so I think we are ready to get going. So let's do this. So today's topic is moments. Hopefully you can all see this screen here. There we go. Well, we'll see. I guess moments might be one of the better ones to see from if you're doing GCSE physics. Because you do moments in GCSE as well, right? I think. But maybe we'll do them a bit differently here. Okay, so we're studying moments. Sadly, our spanner doesn't have a cute little face today, but it's a nice, cute spanner nonetheless. Okay, so the classic, usual announcement, which is that we have a coupon at the end for anyone who wants to check out SnapRevise. We're super proud of what we're doing, and we would love for you to check it out. So stick around to the end, and we'll have a discount code for you. Awesome. So let's just straight in and start thinking about moments. And actually, the first question doesn't exactly mention a moment, but instead mentions a couple. So can anyone tell me what a couple is? This is almost in a way a kind of a funny place to start. And don't worry if you don't know this word or you haven't seen it before. The rest of the session won't require too much memory of what this word is. Most of it will be just about classic moments. But we thought we'd begin by introducing this term. So has anyone come across the word couple? Two equal parallel forces acting opposite to each other. Two forces acting in opposite direction about a pivot. Yeah, absolutely right. Okay, so a couple, and I'm going to draw a picture because I think a picture really is 1,000 words here. Let's say I've got some bar that's going to be pivoting around a point. A couple is a pair of equal and opposite forces. Their lines of action separated by some distance. Good. Not on the same line of action. Good. It's a pair of equal and opposite forces. And you can imagine them as being a thing that is going to cause something to rotate. I exert a force upwards on one side, downwards on the other, and I produce some kind of rotational effect. So this is the idea of a couple. Now, the thing about them being equal and opposite is interesting, because what does it mean for the actual acceleration of the whole object? This is just a bonus question. No resultant force. Nice. Yeah. So a couple is, all we have to say is it is a pair of equal and opposite forces. pair of equal and opposite forces with their lines of action separated by some distance. Good, absolutely right. Really nice. Now the resultant force, whenever you have a couple, you're absolutely right, is 0, because I've got a force F here and a force F here. The total force is F minus F is 0. However, these things do have a rotational effect on the object. Okay, so when we want to talk about a rotational effect, then let's try and be more quantitative. Let's define the moment of a force. This is the turning effect of a force. Exactly right. Yeah. Now, what is the moment as a formula? Absolutely right. M is equal to FD. So the moment M is given by FD. Now, whenever we give something by a formula, by multiplying symbols together, we need to tell the examiner what those symbols mean. So what are F and what's D here? Good. Okay, so F is the force itself. Where F is force and D is distance. Yeah, can we say anything more about this distance? Yeah, it's this kind of, yeah, it's a distance to the point of rotation, but even more, it's what we call the perpendicular distance to the line of action. Yeah, good. Okay. And we'll see what that means in some examples. Perpendicular distance to, it's the perpendicular distance to the pivot point. Good. Okay, so we'll make sense of this in some future examples. First of all, let's work with something where we just need where we don't have to worry about this perpendicular bit because everything's already perpendicular. So here's our first question. Figure 6.1 shows 3 forces acting on a rod. Looks complicated. By taking moments about point X, show that the rod is not in equilibrium when acted on by these forces. So what would it mean for this not to be in equilibrium? So there's 2 types of equilibrium. There's equilibrium where the forces don't add up. Now, we wouldn't need to take moments to know whether the forces all add up. To know whether the forces add up to give a resultant force or not, I could just look at the diagram. And what's interesting about the diagram is we've got 10 newtons pointing down, 20 newtons pointing down, and 30 newtons pointing up. So the resultant force is equal to 0. So it's in what we call translational equilibrium. The force is balanced. So they want us to take moments because the type of equilibrium they're interested in is not whether it's moving or not, like kind of translation-y, but whether it's rotating or not. Good, so there should be a net moment if this is not in equilibrium. If this were in equilibrium, the clockwise and anti-clockwise moments would balance. Okay. So we've got to take moments about point X, and we should just find that we get a non-zero moment, and then we'll be done. So what's the, let's see, what's the clockwise moment? How would I find this? So it's equal to the force times the distance. The force is equal to 20 newtons. And we're doing everything around point X. So we find the distance to X. That's this distance here. And that's 0.6 meters. So together, that would give us, well, what should that be? That should be around 12 meters, shouldn't it? Or 12 Newton meters, in fact. Good. Absolutely right. Good. 12. Okay. What about the anti-clockwise moments? Here, there's a bit more work to do. So, how many contributions are there? Good. So there's one of them. One of the clockwise moments is given by this force, which is at a distance of 0.3 meters from the point about which we're taking the moments. Good. So there's 30 times 0.3. Is there anything else? Yeah, there's another one going on. Another anti-clockwise moment. Well, you could put it up on the right-hand side or you could push it down on the left-hand side. So the one where we're pushing down on the left-hand side is this one here. And that's 10 newtons at a distance of 0.2 meters. Okay, 10 times 0.2. Now, if we look at this, we should be seeing, what's that? So 0.9, so 9 Newton meters plus another 2 Newton meters. So that's 11 Newton meters. So that's all we need to say. By taking moments to show the rod is not in equilibrium. Well, we could just put a sentence for the examiner and say, clockwise not equal to anti-clockwise, therefore not in equilibrium. Good. Absolutely right. Well done, everyone. So, next question. Yeah. Where have we gone? There we are. Figure 1 shows a pole vaulter holding a uniform pole horizontally. You know, I never realized until I was looking at this exam question that there was anything going on to do with moments with like poles. And then I realized, yeah, actually it's impossible to hold the pole by just gripping it at one end. So yeah, I found this one quite interesting. He keeps a pole in equilibrium by exerting an upward force U with the leading hand and a downward force D with the trailing hand. Hey. Okay, here we go. Calculate for the situation shown in figure 1 the force U. Okay, so how can I figure out the force U from this picture? Is there any key words that help us in this question? The key word is we're being told an equation in the form of words. The equation we're being told we're allowed to use is given by this word here, equilibrium. Good. So what we know is that wherever we take moments around, there will be no rotation. The clockwise and anti-clockwise moments must balance because it's in equilibrium, it can't be turning. Okay, so we can take moments around a few places. We don't know D yet. And the classic thing that I'm already seeing this on the chat, so this is fantastic. But whenever you feel like you don't know enough of the forces in a moments question, you can ignore one of them by taking moments around that point. Because then the distance to that force is 0 and you can just ignore that moment. So now we need the clockwise and anti-clockwise to balance. The clockwise is equal to what? I'm going to find the clockwise. So what's the clockwise moment? The force is, it's force times distance, isn't it? Now the force is equal to 200. What's the distance? Good, 1.85. Well done, nice stuff. Okay. Now if you do 200 times 1.85, you should find that that's equal to 340 newtons. Okay. Does that look right? That doesn't look right. That should be 370 newtons, shouldn't it? We made a mistake in our notes. 1 second. Yeah, thank you. It is. It's 370, isn't it? Let me just check I'm not going mad. 200 times 1.85. Yeah, that's 370. Cool. Okay. Good. Yeah, absolutely 370. Good. Okay. What's next then? Well, what are the anti-clockwise moments? Anti-clockwise moments? Well, we have this unknown force, u, and we have to multiply it by the distance. What's the distance? Good, absolutely right, 1.1. 1.1 meters. This u here is a distance of 1.1 meters away from our pivot point, which is at D. Okay, good. Now for equilibrium, what has to be true for these moments? Good. Yeah, the reason for this is what? Yeah, good. Equilibrium implies clockwise equals anti-clockwise. Equilibrium implies clockwise equals anti-clockwise. This is a classic type of question that examiners love to ask. Okay, so 370 is equal to u times 1.1. So u equals 370 divided by 1.1, which is equal to what? Let's see. 370 divide 1.1. Yeah, 336. Looks like a good answer to me. Good. 336 newtons. Awesome. Well done, everyone. Good, absolutely right. And that is indeed the force itself. Okay, now we're asked to calculate the force D. How can we figure out the force D? There's a couple of options, but there's one very quick option. So we know this U is now 336. Good. So we could take moments. We could take moments around U. That would work, but we can do better than this. We can just say that we know because it's in, they haven't said what type of equilibrium, so it must be in both types of equilibrium. So the forces must also balance on this pole. Now, if the forces balance, we know that U must be equal to D plus 200. Okay, so we can rearrange for D. D equals U minus 200, which is equal to 336 minus 200, which should be equal to 136 newtons. Absolutely right. Well done. Good job, everyone. Okay. Next, explain the effect on the magnitudes of U and D if the vaulter moves his hand closer to the center of gravity of the pole and the pole is still in equilibrium. You may be awarded additional marks to those shown in brackets for the quality of written communication. So what do you think happens is that hand that's exerting, well, it won't necessarily be a force U anymore, but what's going to happen to U as the hand moves along the pole? For this thing to stay in equilibrium. So what if the hand was really in here, really over here, exerting some new force, and I won't say whether it's bigger or smaller, U prime. Yeah, so what happens to you? What does you need to be now to create? So the size of you was determined by the moment it made to try and create rotational equilibrium. It needed to balance this 200 times 1.85 moment going clockwise. Now, if u is further away, then it means that the anti-clockwise moment it's making would be kind of bigger because of d. So what needs to happen to u to make sure that it was the same value of the moment of before? Good. If once we move further away, the same force would have a bigger turning effect. We want it to be in equilibrium, so we now need to decrease the force again. Good, absolutely right. We want to keep the moment constant. That's another way to think about this. Moment equals u times d. We want to keep this constant, which means that the moment is kind of proportional to 1 over the distance. So yeah, as the distance increases, we need the force to decrease to keep this thing in equilibrium. So first thing that we say is u will decrease. U will decrease because as it's further away, a smaller force will create the same required moment for equilibrium. What will happen to D? What's going to happen to D here? If U has decreased. So we know from the equation we wrote down before, what was it? D plus 200 would be equal to U. What happens if U goes down? What does that say for D? Yeah, absolutely right. This equation here says that D is actually proportional to U. If you look at this diagram here, if the upwards force is a bit less, then the downwards force that we need to keep this thing in equilibrium will also be a bit less. We don't have to do as much work to balance this upwards force anymore. Good. Okay, so D will also decrease since D equals U minus 200. If you decrease U, you decrease D. Good, absolutely right. Well done, everyone. Kind of a hard question. So, okay, next one up. State the principle of moments. So we've used it a couple of times, but let's actually just say it all out loud. What's the principle of moments? Yeah, when is it that the clockwise and anti-clockwise moments are equal? Good. So that is one part of it, but we have to say when that's true. In equilibrium. Absolutely right. Awesome stuff. Well done, everyone. So the principle of moments says that the sum of the clockwise moments is equal to the sum of anti-clockwise moments when the system is in rotational equilibrium. Awesome. There we go. Good, absolutely. So that is the textbook answer. If we can remember that by rote, not only will it be useful in helping us answer questions, but it will also earn us these particular marks for giving the right definition. Awesome. So we mentioned couples before, and let's go back to those a bit. They're just a special case of moments that can be kind of particularly interesting because they turn up a lot. Okay. Horses were once used to power machinery in factories, mines, and mills. Okay, figure 5 shows 2 horses attached to a beam which turns a wheel. This wheel drives machinery. Okay, each horse exerts a force of 810 newtons, and the length of the beam is 7.3 meters. Define the moment of a couple. So what would you say? Find the moment of a couple. It's kind of a funny thing because it's just equal to finding the moments. But there's another way we can say it now when it's a couple. Yeah, so I mean, the moment of a couple should be whatever moment this couple is producing. But one way to kind of talk about this without kind of talking directly about the pivot is to say, well, it's the force by one of them of one of the forces times the perpendicular distance between the forces. Now, this seems kind of odd. It's actually kind of worth thinking about. Okay. Usually, if I was in a situation like this, how would I find out the moment? Well, I'd have the pivot here, and I'd say, okay, well, the clockwise moment is being given by 810 newtons multiplied by 7.3 over 2. Okay, and here I've got another 810 newtons multiplied by 7.3 over 2. And then I'd add them both together, and I'd end up with 810 newtons multiplied by, well, 810 newtons times 7.3 over 2 plus 7.3 over 2 equals 810 times 7.3. And that's what this definition here said. Take the force of one of them and multiply by the distance between the forces themselves. Good, so there's kind of 2 ways of calculating the moment when you have a couple. Now, the funny thing about a couple, and it's worth kind of having a go at this in your own time, and this is kind of the cool thing and why we state it like this, is we don't have to mention where the pivot was. So if the pivot had been someplace not kind of equal between them, then you could still find this moment and it would still be the same. The moment around this point would still be given by 810 times the distance between the forces. So there's a kind of funny thing going on there. Anyway, we won't need to worry about this too much here, but I just thought I'd flag that for you. So the force of one of the forces multiplied by the distance between them is the moment of a couple. What if D1 was not equal to D2? Exactly, you'd still get the same result. Exactly, good question. Yeah. That's the kind of surprising thing about the moment of a couple. We won't need to use that here because we do have D1 equal to D2. Okay, so we can ignore all of this anyway when we're asked the next question, which is to calculate the moment of the couple exerted by the horses. So you can just calculate the moment in whatever way you like to here. It's a clockwise moment, and we already kind of mentioned how to calculate it. So you could either choose to do 810 times 7.3, or if you prefer thinking about moments in the normal way, just add this clockwise moment here to this clockwise moment here. That would be 810 times 7.3 over 2 plus 810 times 7.3 over 2. Half the distance and calculate the moment of both. Exactly right. That's this second option here, which in a way I kind of think is simpler to think about. Yeah, good question. Okay. So altogether, we find either way that it's equal to 810 multiplied by 7.3. And we can chuck this into our calculator, and we should get around 5,900. And what's the units here? What's the units of a moment? What's the units? I'm not sure if we mentioned this yet. Yeah, good. Newton meters. Good. Good. Great. Okay, well done. So let's have a look at another question. I think this is kind of a cool one. A sprinter is shown before a race, stationary in the set position, as shown in figure 4. Okay, good. So they're in that bit where they're kind of docked and ready to go. Force F is the resultant force on the sprinter's fingertips. Okay. The reaction force Y on her forward foot is 180 newtons. Okay, let's label that in because they haven't labeled it for us. 180 newtons, that's Y. Always do that. If the diagram they've given you doesn't have all the information, label it all on there. It will often make the question easier. Her weight is 520 newtons. Okay, 520. X is the vertical reaction force on her back foot. Okay, so this one we don't know. Calculate the moment of the sprinter's weight about her fingertips. Give an appropriate unit. Okay, so how could we figure out this moment? The moment of the weight about the fingertips. What force? Well, the force must be the weight, but what's the distance? What's the distance that we need to use? Yeah, so we're using X as a pivot, absolutely right. The moment about her fingertips. Well, her fingertips are, sorry, not X, no. Sorry, my mistake. About her fingertips, where are her fingertips? Her fingertips are here. They're where F is. We need to calculate the moment around this point. Good, so the distance between the line of action of the weight, the perpendicular distance between this kind of line of action and this point here is, well, that's this distance here. And this distance here is equal to what? 0.26 meters. Absolutely right, good. So the moment is equal to weight times distance, and the particular weight is 520. And the particular distance is 0.26 meters. So we should be able to plug these in together and get 140. And as you've just told me, the units are Newton meters. Good, absolutely right. Yes, so in fact, in more detail, this is 135.2. Good. Aha, okay. Yeah, let's talk about it. So the moment is equal to the distance between the line of action of the force. Okay, so where's the force? The force is the weight. I draw its line of action everywhere because I want to try and figure out the distance. And the distance is basically the shortest distance between the point that we're taking moments around, which is this point here. This is the pivot. We want to find the distance between this point and this line of action of the force. So what's the shortest distance? Well, it's not going to be one of these distances or one of these distances. It's this perpendicular distance. That's the shortest one. Now, what is this distance? We're just looking for the distance between, whoa, sorry. 1 second. I've just accidentally started subtitles, which we probably don't want. That was interesting. Sorry, 1 second. Sorry about that. Okay. Sorry, I'll just be back with you all in 1 second. Yeah, I don't think you needed to see my voice subtitled at the bottom. Okay. So I think we're back, which is good. Good. Okay, so we're back and we're asking about this question. Yeah, so we're taking moments about the fingertips. That means the fingertips are the pivot. This is the pivot point. Okay. Now we want to find the distance between the line of action of the force. We want to find the distance between the force and that pivot point. And that distance is this 0.26 meters. Ah, awesome. Cool. Great. Okay, good. Well then, the fingertips are the pivot. Absolutely right. Good. So it's kind of cheeky. They're kind of trying to confuse you by putting a lot of real life stuff in to A, kind of keep it interesting, but B, to make it kind of harder to figure out what the kind of the things that you actually need are. Yeah. Okay, good. Well done. Okay, so that's our answer. So next question. By taking moments about her fingertips, calculate the force on her back foot marked X. Okay, so we're still taking moments around the fingertips. So this is our pivot. Okay. That's our pivot point. Now, we calculated the moment due to the weight already. What was that equal to? Does anyone remember? Ah, nice, way ahead of me. So this moment here was 135.2. That was a clockwise. Now, what principle are we using? Good. What principle are we going to use to calculate the force back here? So if we want to figure out this force, we need some kind of an equation that tells us something. Now, we're being told she's stationary. Because she's stationary, that's the same thing as saying she's in equilibrium. She's not moving, she's not rotating. So what this means is that we can use the principle of moments. Clockwise equals anti-clockwise. Okay, so what are the clockwise moments? There's only one of them. It's this 135.2. What are the anti-clockwise moments? Good, absolutely right. The principle of moments. Absolutely right, really nice. Okay, so the anti-clockwise moments, there's two of them, isn't there? Good. See, because, yes, it is like that, but we need to put the distances in. Absolutely right. 1352. Ah, so this was from the previous question. We calculated the moment of the weight around the fingertips already. That was this question here. And we said it was 135.2 by taking the weight, which was 520, and multiplying by the actual distance, which was 0.26. Cool. Okay. So we know this clockwise moment due to the weight, and we need to find the anti-clockwise moments. We were told this reaction force, 180. So what's the moment due to y? I'll just kind of rub this out so you can see the distance. Good, absolutely right. The moment due to y is the force y multiplied by its distance from the pivot. What's the distance? 0.41 meters. So it's 180 times 0.41. And we need to add this to the moment due to x. Now, x, we don't know the actual force, but we know the distance, 0.63. Good. So then altogether, we can rearrange for x. So x will be equal to, well, it's 135.2 minus 180 times 0.41, all divided by 0.63. So that's just rearranging this equation so that we're ready to put it into a calculator. And you should find that this is equal to 97 newtons. Good, absolutely right, yeah, 97.46. That's roughly right, good. Okay, so one last question. Because it's actually amazing what you can figure out from this question. There was so much that it felt like we didn't know at the start. But now we can calculate the force F. So how can I calculate the force F? I know that this is 520. I know this is 180. I know that this X is 97. How can I calculate F? What principle can we use here? Good, so here we know three of the forces, we just need to know the fourth. They're stationary, so not only are they not rotating, but they're not moving. As they're not moving, the resultant force must be balanced as well. Good, yeah. So if the forces are in equilibrium, just like with moments, you balance clockwise and anti-clockwise. With forces, you balance up with down. So the upwards forces are what? What are the upwards forces? One of them we don't know, so we can leave it as just a symbol. So this upwards force we don't completely know yet. We know some of it. We know it's F plus Y plus X. That's the upwards forces. The downwards forces are W. Now, luckily we know three of these numbers, so we can plug them in. So you're absolutely right that that is also going to be the answer, Takia. Yeah. So here we're fine just to actually balance the forces themselves. The upwards forces must be equal to the downwards forces. The upwards forces are F, Y, and X, and the downwards force is W. Good, so altogether we find that F plus 180 plus 97 must be equal to 520. So then F is equal to 520 minus 180 minus 97. And you should then find that F is equal to what? Well, I found that this made F roughly equal to 240. Depending on exactly what the decimals are that you've carried over from each bit of the question, it could have been between that and around 242.5. Which Takia got exactly. Yeah. Yeah, does everyone get an answer around there? Is there any questions about that bit or any of the stuff that we've seen today? You're 243. Cool. That's chill too. Yeah, any questions about that last question? Oh, good. Okay, well done everyone there. That was really good stuff. It's always really good when there's a lot of back and forth. It helps me to see how all of you are doing, and it helps me to pick up on any questions you have. It's absolutely great if you're asking questions. Never be scared to. It's really interesting, and it helps us see how it's going. So yeah, thank you very much for today. Thanks for making it really enjoyable. We do have a coupon code. Yeah, and thanks everyone for coming. Actually, yeah, it's really fun session for me. I enjoyed that. So yeah, thanks for staying engaged. Yeah, so we have a coupon code for you all, but just before I go through that, I'm just going to slam through and show you some of the details of SnapRevise itself. And we can even probably find a quiz that tests us on all of the stuff that we've just seen. No, thank you for coming. Cheers. Okay, so I'll just take you through quickly a quick walkthrough of the SnapRevise website. So this is a product that we're just like insanely proud of right now. We've been putting together all sorts of stuff, and we've been putting together considerably more sessions since all of the virus stuff as well. So in particular, I am now doing loads of these web classes. So I do two a week here, which I really enjoy doing in YouTube. But I also do another 6 a week at the moment on the SnapRevise website. We do a couple where we go through set material and we discuss it together, and we try and iron out any issues that anyone has. And also we do a couple which are called drop-in sessions. Now the drop-in sessions are great. There's no structure to them. So you can just come in with questions, anything you're confused about, and I and kind of the group will all work through it together, and we'll make sure that we can all come out understanding. Typically it's things like exam questions that you can't figure out the answer to, etc. Now SnapRevise is a lot more than just the web classes as well. Aside from the web classes, we've got some fantastic learning resources. We filmed video courses to kind of feel like tutoring for example, for physics, we've done this for all of the exam boards, and we've done the same for maths and chemistry and biology and so on. So we're really proud of what we're doing. And I'd just like to show you a bit of it. So I can go into our A-level physics course, for example. And one of the things that we're really happy with at the moment is this section that we've included on smart adaptive learning. So the idea of smart adaptive learning is that we've introduced, let's go for the moments quiz. This seems like the right quiz to look at. The idea of smart adaptive learning is this. You get a quiz and it doesn't just tell you how you did, but it tells you exactly what you need to learn, and it points you exactly to the bits that you need to work on. So it takes you through our SnapRevise course, but it gives you your own unique route through it, depending on how you're doing on the quizzes. The idea is that this should streamline your learning. You don't want to actually spend time learning stuff that you already know. You want to make sure you streamline and make sure that whenever you're revising, you're actually learning. That way you can spend less time revising as well, and more time out in the sun when all of this madness is over. Okay, so let's take a look at a quiz, because this is such a good idea. Okay, what's the mass of a ball weighing 25 newtons? How do you figure this out? Well, it should be that divided by about 10, shouldn't it? Because gravitation acceleration is 10. Good. Okay, let's have a go at another. Mass of a probe is 17 kilograms. Its weight is this. Acceleration due to gravity on this planet. Acceleration due to gravity is weight divided by mass. So what's it's something like 100 divided by 20, which is what, 5-ish? Let's go for that. Yeah. Okay, now let's just guess a couple of random ones. And if we see a good question, maybe we'll stick on it for a bit. Where is the center of mass of an object located? What do you reckon? I reckon it's that. Same as the center of gravity. Good. Okay, Mike wants to open a door by pushing it. This is a good question. Which of the following actions will produce the largest moment on the hinge? Okay. Large force far from the hinge, large force close to the hinge, and the other options. Well, we know this is biggest force, biggest distance from the hinge. Force times distance is the moment. Amazing. Okay. We'll look at a couple more, guess a couple. Okay, now it starts to get a bit more quantitative, tests that we can really use the formulas, etc. And this really doesn't take long to go through this kind of quiz, which is good. Something you can do at any time because it will save your progress. Okay, so we're nearly there. Rod does not turn. How far is the center of mass? Whoa, I don't know. That one. Nah. Rubbish. I'm sure the following pairs of forces is a couple. Oh, this is cool. We talked about couples today. North and east. It's got to be that. Yeah. Okay. No good. Fine. Okay. So here's where the good stuff happens. I smashed through this quiz. And, well, I say smashed. I got 43% on this quiz. Now, typically, this is where this sort of thing ends. And maybe you would even get a summary like this kind of thing from some kind of quiz. And this would be great because you go away and you have a rough idea of what you've done. What would be even better if the course now changed to suit what you need to actually be doing? So if you take a look at what we get taken to here, we get taken to our video courses. And this is where stuff gets really good. So here, if we look at the videos on the left-hand side, well, notice that some of them are highlighted in orange and some of them are highlighted in green. Great thing about this is that, okay, so these colors are based on the results of our test. The green video is one that we just don't need to watch. We smashed all the questions on that stuff. We don't need to learn this stuff. We got it down. So we can just go to the orange videos. We go to the orange videos in order. And not only do we go to them, but SnapRevise will tell us which bits of the videos we need to watch, because there's bits inside here that we answer questions correctly on, like the equation for weight, but we didn't get Newton's second law right. So we do need to learn this first bit here. So one of the main ideas here is really like a time-saving thing for you. There's only so much you can spend your time learning. I'm sure you've all at some point felt overwhelmed by the amount of revision you feel like you need to do. Well, this is our solution to this, figuring out exactly the details and the bits that you personally need to do. Okay, now you notice that we also have exam questions that you can walk through and have a look at. So we produce exam packs, but also of our own exam questions. But we also thought it would be useful to show you how we personally would have a go at some exam questions. So we've made some exam questions and we've done videos of ourselves going through the questions to show you how you should think about them and how to extract information from those all too tricky examiner written questions. Okay, so as you can see, there's a lot of stuff going on. It tells me how far through the course I am as well. I'm doing okay. So I just want to show you our plans so you have an idea of what we do. The idea for us was tutors are £50 an hour. Tutors can be around £50 an hour. This is a completely inaccessible cost, like a regular cost for lots and lots of people. So we figured, what can we kind of do with a chunk of £50 and spread out over a much longer time? So we thought, rather than £50 an hour, can we offer something better than the tutoring experience for less money? How about £50 a month? That's way better. Okay, so that would include all of this web class stuff that I was talking about. But we have much cheaper options as well. So in the basic option, we're talking £10 a month. And for the £10 a month option, you have access to our teaching resources, which we're really proud of. We spent so much time making these videos courses. They're what we started doing originally. Yeah, we spent years on these things and we really love them and we hope that you'll love them too. Now in the pro section, we've introduced this smart adaptive learning to try and speed up your learning and try and streamline your learning. So these self-marking quizzes that take you directly to the bits of the course that you need to see, along with some packs of predicted exam questions that we've come up with. We're trying to guess what we think are the most appropriate questions that an examiner would want to ask you. Finally, if you're interested in the web classes and stuff, which we're really happy with, we figured, okay, that's a real like the tutoring experience, but tutoring is just not affordable. So we decided to take £50 an hour and move it to £50 a month. And so for a month, I mean, how many classes do? I do six classes on SnapRevise a week, plus the 2 on YouTube. So we're talking what, 18 hours of tuition for the same cost as, I guess, essentially one when someone like myself would be tutoring privately. So we think this is a really good kind of scalable model and try and open that kind of teaching up to as many people as possible. I love doing the web classes, and I'd love to see any of you here in any kind of capacity in any way possible. Aside from that stuff, I really hope I get to see you all in the next YouTube session as well. Now, thanks for sticking around. Thanks for taking a look with me. I hope it looks interesting. We're really happy with it. So there's some new home study clubs coming up. So set yourself a reminder on YouTube. We'd love to see you there for these. We're doing biology, maths, and chemistry as well. And finally, here is the discount code for today. So here is our discount code. So yeah, let us know if you have any questions. Okay. Yeah, good question. I believe it is per subject. Let me just check that with you. Let me just check that for you. Okay. Yeah, it's per course, I'm pretty sure. Okay. Let me just see. I'm just having a look now. AQA. Yes, absolutely right. It's per course. Mm-hmm. Cool. Yeah, I'm afraid I don't know enough about hemoglobin. I wish I knew more biology, but I'm very much at my limit with GCSE. Okay, great. Thank you very much, everyone, for coming, and I will see you later. Great. Thanks very much, everyone. Cheers. Bye.